Lord.
Does it?
How's everyone doing today? All right. This should be a normally scheduled week. Lecture all 3 days and also lab. Lab this week should be very interesting because we will be firing marble cannons. So, follow all safety rules for that, please. Now, as for lecture, last time we began chapter 5, which is just an exploration of Newton's third law of motion. We'll work on that today, possibly begin talking about chapter 6 as well. These first couple are all pretty rapid fire. They're only called different numbers because the textbook orders them as such. Before we get started on that, people have been sending in their labs, which is great. I've been giving feedback to all of them, either in paper or electronically. If I give you feedback for something to fix, it is totally okay for you to take time to fix it. I would say in that case, it's a very soft due date. Like, as long as I have tell you something to fix, it's fine for you to then get back to me with it later. Just keep handing it in until it is what I deem the A that you would normally get before you leave the normal lab. So if I tell you something to work on, it's okay to keep working on it, even if that takes time. Does anyone have any questions about that before we move on today? All right. In that case, let's resume our discussion of Newton's laws on Friday. Brain waking up. We began specifically looking at Newton's third law. This is the third of the three. We've been spending the last couple of weeks looking at each one in turn. Just to quickly glance at them again, because again, you do have to be able to identify them by number on the first test, which is coming up in a couple of weeks now. I promise we'll review that in class as we get closer. Laws of motion in order are inertia, acceleration, and action-reaction. Now, what Newton's third law tells us is that every single force ever, kind of by necessity, causes a reaction force to be generated. Because forces can't just exist by themselves. Force always has to be one thing acting on a second thing. You can't just have a force pop into existence completely isolated from other things. It always has to be something acting on something else. And Newton's third law tells us that by necessity, the second thing acts back on the first thing. So every single force ever is part of an action-reaction pair. All forces must come in pairs. And the way that the pairs work is, I describe it as, if A on B, then B on A. It is always a complete reversal of which object is the recipient, which object is the source, and the direction the force acts in. And we looked at a couple action-reaction examples. Today I want to kind of go through some of the finer quirks of Newton's third law and how action-reaction pairs work to make sure that this concept is fully ingrained in your mind before moving on. There's a couple specific oddities to this that I want to make sure make sense to you. Any questions about that? Brief review before moving on. All right. Now, action-reaction piece of trivia number 1. This law requires that the force the two objects exert upon each other is the same. The force is the same, even when it doesn't necessarily feel like it would be the same. A pretty good example is cannon fire. The force between the cannon and the cannonball is identical. However, you wouldn't be faulted for thinking that they aren't quite the same force. Why might that be? If you look at this happening, does it feel like one of these two objects has a bigger force acting on it than the other? Yeah, which object feels like it probably has more force acting on it? Cannonball. Yes, I promise I'm not trying to trick you. It kind of feels, looking at this scenario, that the cannonball itself probably has a bigger force on it because it is what rockets off into the distance, right? A cannonball is designed to go shooting that way. However, there is still a force on the cannon equal and opposite to the cannonball. If you've ever been around cannons or perhaps watched a pirate movie, have you noticed that the cannon itself tends to get knocked backwards as a result? Maybe not nearly as much as the cannonball gets knocked forwards, but the cannon does still recoil, correct? That recoil is a result of the force that the explosion and the cannonball exerts back on the cannon. I'm trying to see what marker color would be the most visible here. So let's say that the cannonball has a 2,000 Newton force blasting it forwards. There therefore must be, according to Newton's third law, a 2,000 Newton force on the cannon recoiling it backwards. Excellent cannon, wouldn't you agree? Now, it's the same force, but you get a different reaction because the objects just have different masses. Cannonballs aren't light, but the mass of the actual cannonball is much smaller than that of the cannon. Usually, like in ye olden times, they'd both be made out of cast iron. The cannonball is this much cast iron, and the cannon is this much cast iron. It's just got a way bigger mass. Even 100 times the mass would necessitate 100 times less acceleration. Remember, F equals ma. The same force on two different masses causes different accelerations. If the mass of the cannon is 100 times bigger, the same force would cause 100 times smaller acceleration in the cannon. So that recoil is still the result of the force of the explosion recoiling the cannon back, but the increased mass of the object just makes it have less of an effect. And it's not just vintage weaponry that will do this. This happens pretty much all the time. For example, I am now going to throw this golf ball at the wall. It's going to make a noise, so you've been warned. Same basic thing just happened. When the golf ball hits the wall, there's going to be a force both on the wall and on the golf ball. The golf ball is going to accelerate a lot. It accelerated enough to change direction. So the force from the wall on the golf ball was pretty significant. Would you call the force from the golf ball on the wall very significant? No, the wall doesn't budge, does it? But the ball still exerts a force on the wall. It's just the wall is part of a building with like 10,000 times the mass. And so the building's not going to go anywhere when I throw a golf ball at it. So it still received the same amount of force, it's just it didn't do anything because of the mass difference. One last example I would bring up is if you hit a bug with your car. 1 Newton of force annihilates a mosquito, but your car doesn't notice. So, even if it doesn't look like there's an equal and opposite exchange of force, there is. If it doesn't look like it, odds are the masses are just very out of balance. How's that feel? All right. Second piece of Newton's third law trivia that I think you should be aware of. We've talked about normal force before, correct? We've been describing normal force as what happens when you press into a surface, therefore it presses back up on you. We've been describing it as the force that keeps you from falling through the earth, keeps you from falling through your chair. Normal force is, by definition, a reaction force. The normal force, support force, happens because of Newton's third law. in the case of this boulder sitting here, the boulder presses into the ground, therefore, as a reaction, the ground pushes back up on the boulder. Every time there is normal force, it's because of Newton's third law that normal force is always just a reaction to the surface being pressed into. So we've kind of already been talking about Newton's third law. Like, all the laws are connected. You kind of can't talk about one without talking about the others. But something else to note about normal force while discussing it is that normal force, I mentioned very briefly that I call it normal force because of the math definition of the word normal, which is just a synonym for perpendicular. Sound familiar? It's okay if not. Brief review if that doesn't sound familiar. If you ask a mathematician what normal means, they'll say it just means perpendicular. In math, normal means perpendicular. So really this is the perpendicular force. And we call it that because surfaces, if you press into them perpendicularly to their surface, are only able to act perpendicularly out of themselves. If I press vertically down into the horizontal ground, it acts vertically upward on me. Surfaces can only exert forces perpendicularly out of their surface, and as a result, they are only able to react to forces that point perpendicularly into them, since normal force is a reaction force. Now, if I press 5 newtons into the ground will act with 5 newtons back up. But the ground is only able to respond to forces that are perpendicular to itself. It's only able to push out perpendicularly as a response to things acting perpendicularly into it. If I try to exert a force parallel to the ground, I'm not really pushing into the ground, I'm just dragging something along the ground. And that's no longer the realm of normal force, that's the realm of friction, which is something else. All surfaces only respond perpendicularly because something pushed into them perpendicularly, which kind of creates a weird situation on slopes. I've got here a box sitting on a ramp viewed from the side. Slopes are kind of weird because on a ramp, gravity still points straight down. It doesn't have any other choice. Because even if you're on an incline, Earth's core is still down there. So on a ramp, gravity still points straight down. But gravity is no longer perpendicular to the surface. The surface now points this way, perpendicular points that way, and gravity's not pointing that way. The normal force from the ramp can only point perpendicularly to the ramp. So on a ramp, gravity still points down, but normal force points out this way, perpendicular to the ramp's surface. This kind of thing really only happens on ramps. It's a very weird interaction. But what it means is, on a ramp, gravity and normal force cannot cancel out because they don't point in opposite directions. The normal force is tilted. You see how that picture works? Since they cannot cancel out, they're not going to add up to 0. And this is why things slide down ramps. If they don't add up to 0, there's going to be a net force. And down, added with slightly up and slightly right, points that way. So the reason things slide down ramps is because normal force is only equal and opposite to the amount of force going perpendicularly into the surface. Things that slide down ramps, because on a ramp, normal force and gravity are not equal and opposite. I'm bringing this up, one, because it kind of explains why things slide down ramps, which I feel is useful to know. But the other reason I'm bringing it up is to make sure you are aware normal force and gravity are not action-reaction pairs. That is a rule. Gravity and normal force are not action-reaction pairs. By definition, they cannot be, because this situation exists. This is a situation where these two forces are neither equal nor opposite. To be third law pairs, you have to be both equal and opposite. And on a ramp, gravity and normal force are neither to each other. Very often, on a flat surface, gravity and normal force will be equal and opposite, but they are not equal and opposite by inherent trait. They're not third law pairs. They are not always equal and opposite. How's that sound so far? If the two are equal to each other, it's a coincidence. It's a nice coincidence. Again, it keeps us on the ground, but they're not third law pairs. The third law pair to normal force is just whatever force was pushing into the ground. The ground doesn't care what that force is, because the ground doesn't know. Your chair doesn't know. Which brings me to the last piece of third law trivia I'd like you to know this chapter. If normal force is not the reaction force to gravity, what is the reaction force to gravity? The secret answer is more gravity. The reaction to gravity is gravity. On Friday, we looked at, I gave you several scenarios that involved force, and I asked you to identify the third law pairs here. One of those scenarios that I mentioned is a rock falling towards, freely falling towards the ground. This is not a scale drawing. This is the earth, this is the rock, this is not to scale. But this rock is going to fall towards the ground. What force causes the rock to do that? Gravity. Promise, not a trick. So that is the gravity of the earth acting on the rock. I'm going to label it as such. Gravity, earth on rock. That's the force that causes the rock to fall. Whatever else is going on, air resistance or not, parachute or not, that's the force that's pulling the rock towards the Earth's surface and also its core. Based on the logic we've established for how action-reaction pairs work, what is the reaction to this force? Gravity of the rock pulling on planet Earth. Just as the Earth pulls the rock towards it, technically the rock pulls the Earth towards it. You have your own gravitational field. If I weigh 1,000 newtons on planet Earth weighs 1,000 newtons on planet me. I am in a way a planet, and the Earth is living on my surface, or at least on my feet. Now, kind of referring back to piece of trivia number 1 from a few slides ago, you will never really notice the force you exert on planet Earth because the Earth's mass is literally, what's the mass of the Earth rated at? 10 with 25 zeros times bigger than you. So going back to Newton's second law, 1,000 newtons on a mass that big, infinitesimally small acceleration. You will never notice the Earth accelerate because of the force you exert on it. Ignoring the fact that there's also billions of other humans on every other square inch of the surface pulling it in every other direction. So even if you were the only human on Earth, this acceleration would be minuscule. And since you're not the only human on Earth, it all just cancels out. But the reaction force to gravity is more gravity. If Earth's gravity pulls on the rock's gravity pulls on the Earth. And again, you'd never notice that normally, but there is one major case where you do perceive it, and that is actually with the moon. You know how the tides work? The moon's gravity pulls back on the Earth, like how the Earth's gravity pulls on the moon. And since the Earth is so much bigger than the moon's not really able to tow the Earth around, but it is at least able to drag the oceans towards itself. I'm going to kind of repurpose this picture here. This is still not to scale because the moon is much smaller than Earth and also much further away than this. But the Earth's gravity pulls the moon towards it. That's why the moon orbits the Earth. The moon's gravity acts towards the moon. Again, the Earth is too big for the moon to be able to move it, but what the moon does is it slowly pulls all the oceans to this side of the planet. And as the moon circles, this extension of water circles the entire planet. So if you're on this side of the planet, it's high tide, and this side of the planet is low tide. So, evidence that the moon's gravity affects the planet just as the planet's affects the moon's. The moon, singular. So, the reaction force to gravity is not normal force. The reaction force to gravity is still more gravity. How's that feel? All right. So, very quick example. Here we have a rock at equilibrium. What forces can you identify acting on the rock, and what are the action-reaction pairs of all those forces?
Gravity pulling the rock down.
Very good. Earth's gravity pulls down on the rock. What else acts on the rock? Earth's surface, yes, pushing up on the rock, force normal. So I promise this part's not a trick. These are the forces we've looked at before. Now, in this scenario, they're equal and opposite, but they're not a third law pair. They're not a third law pair for several reasons, one of which being, again, normal force and gravity are sometimes able to be not equal and not opposite. So those two forces aren't a pair to each other. Each of those single forces has their own pair. But those are the only two that act on the boulder. So we have identified the forces acting on the boulder. That said, the fact that they're both acting on the boulder is further proof they're not a third law pair. Because again, the rule for third law pairs is if A on B, then B on A. So third law pairs always act on different objects. Therefore, they cannot act on the same object. According to this statement, the third law pairs must work on different targets. First, B is the target, then A is the target. These two forces both act on the boulder. Further evidence that they can't be third law pairs. Instead, each of these single forces has its own third law pair. What is the third law pair to this gravity? If Earth's gravity pulls on this rock, therefore, rock's gravity pulls on Earth. Why do I keep giving me that? So that is the third law pair to the weight of the rock. This is the force acting on the rock. This describes the reaction to that. Separately is the normal force acting on the rock. So, separate interaction, if Earth's surface pushes up on rock, therefore what? If Earth's surface pushes up on rock, rock pushes down on Earth's surface. Now, the Earth is involved in both of these, but it's a different force from the Earth in both cases. In this case, the rock pushes into Earth's surface, meaning the dirt at this location. Therefore, the dirt at that location pushes up on the boulder. Here, the gravity isn't necessarily being caused by this patch of dirt. It's being caused by the molten core very far beneath us. Gravity always comes from the center of mass. So this is the center of the Earth exerting a remote field force on the boulder. Therefore, the center of the boulder exerts a remote field force on the center of the Earth. This is the surface of the Earth touching the surface of the boulder. There are different types of force. And again, further evidence normal force and gravity are not third law pairs. The dirt doesn't really care why the boulder is pressing into the surface. It just cares that the boulder is pressing into the surface. And so it will respond to that. To kind of cast another analogy here, your bathroom scale doesn't care why something is pressing into it. It's just going to read a number. You know what? Not even bathroom scale. The fruit scale at the supermarket. Those still exist, right? The fruit and vegetable scale at the supermarket. It doesn't care what is pushing down on it. It just responds to being pulled down on. You could put like a pound of apples in there. It knows there's a pound of force pulling down on it, so it will read 1 pound. Because that's the amount of force that the scale notices, that's the amount of force it has to exert to hold up the basket. But separately from the weight of the apples, you can just grab the scale and pull down on it, right? And then the number's gonna increase. I definitely played that game as a kid where I would grab it and try to max it out. I'm not the only one, right? Now, if you're doing that, it's not that there's any weight in the basket making the scale max out. The scale doesn't care that if gravity is what's pulling on it or not. The scale just cares something is pulling. I must respond accordingly. And frankly, all a scale ever does is it tells you the force it's exerting. It doesn't care what's acting on it. It just cares that it's being acted on. It's why you can change the value of a bathroom scale by either using a counter to push harder into it or use the counter edge to lift you up slightly. The scale doesn't know how much you weigh, the scale just knows how much force is acting on it. And then it responds. Normal force doesn't care whether it's gravity or not, it just responds. If I press, kind of like the dictionary question in the remote lab from last week, if I take anything and push harder down on it, normal force has to increase to overcome that. It doesn't just increase the gravity, it just responds to whatever lump sum of force is being exerted into it. It doesn't care if it's gravity or not. I feel like I'm overemphasizing this point. I think I'm just on a rant. How's this feel? All right. Any questions about Newton's third law or the laws in general? All right. Well, congratulations. You've studied at least the first physics laws of this course. And now we're going to spend the rest of the course using them. As an example of that, I want to at least segue into what the rest of the week will be about. This is again what the book would arbitrarily call chapter 5. The first several chapters have been about Newton's laws. So now what the book calls chapter 6 is beginning to apply them to specific circumstances. And kind of in keeping with the fact we just talked about Newton's third law, action, reaction, things exerting force on each other. Where'd it go? I've got too many PowerPoint tabs open at once. Chapter 6 will be about things slamming into each other. And as a result, so will next week's lab. This week's lab is cannons, next week's lab is things colliding. So, should be an interesting couple of weeks. So, the main things for the rest of this week will be momentum, impulse, and collisions. Those might sound like all new concepts, but I promise they are a direct continuation and application of Newton's laws. Sound fair? Every single thing, basically every chapter is going to build right off of what we just did in this class. So, who's heard the word momentum? Well, okay, first before I do that, any questions, needs, concerns from you guys before we slightly switch gears? All right. Now, who's heard the word momentum before? Okay, good. Who could define the word momentum? Don't throw your classmates under the bus or under the train. Push. There's forces involved, definitely. There's forces involved with the transfer of momentum. How, yes?
Like the strength of like the motion you're doing, or like how?
That is a pretty good summary, yes. I'm gonna hold on to that. That's a good way of describing it. Before moving on though, separate question, how do you hear the word momentum kind of used in English just every day when it comes up? Even if it's being used as a metaphor.
In sports.
Sports? How do they use it in sports? What do the analysts say?
Using their momentum.
Using their momentum? Okay. Yeah, the athletes tend to build up momentum as they're running forward to slam into things and other people. I've also heard sometimes that a team might build up momentum throughout a season, like keep up their win streak or something like that. Sound familiar? Okay. As far as physics words being used in everyday English goes, all of that is actually not a bad description of the physics definition of the term. The physics definition of momentum is a vector measurement of how difficult a moving object is to stop. The more momentum something has, the more difficult it is to bring it to a halt. To tie that into some of the points that you guys just made, the more momentum something has, the more force it will take to stop, and the more force it will exert if it slams into you. So, yes, that ties into what one student said. Separately, if you have more momentum, you are more difficult to stop. Again, like the athlete running down the field, or the team that has a good win streak and is on fire. So again, surprisingly good use of the term, in my opinion. Now in physics, we consider momentum to be a vector. That means it points in a specific direction. So within physics, if something is moving in a direction, we know that it wants to keep moving in a direction, and it's going to take effort to either slow it down or make it change direction. So momentum is a vector like velocity and force and other things we've discussed. Now momentum is a thing we can measure, and that means it's a thing we can calculate. So it has a variable symbol and an equation. This equation reads, an object's current momentum level is equal to its mass times its velocity. Now I do appreciate that the words momentum and mass both start with M. There's only one m in the equation, and it's still being used for mass. This thing on the front looks like an English letter P. That is the symbol for momentum, because physics ran out of alphabets a long time ago. We don't use uppercase M for momentum, because sometimes we use uppercase M for mass. Instead, we stole from the Greeks and applied the Greek letter rho for momentum, which I'm sure made sense to someone several hundred years ago. So that, it looks like a P, but it's not technically an English P. It's the Greek letter rho. There is not any Greek organization on campus that uses that letter, is there? And I didn't remember one. Now, I believe that rho is, yeah, you know what, I don't speak Greek, I shouldn't say it like that. What I will say is that rho looks a lot like an English letter P. When I write them, the main difference is that P has the stem on it and rho doesn't. Rho is basically a circle with a tail. And P is this. And they are both further distinguished from uppercase English P, which is another unit entirely, power, which is what next week will involve. So that's, that makes sense. I'm addressing all of this because, out of habit, I am going to read this equation as rho equals mv. And I want to make sure that that makes sense to you when I inevitably say it out loud. So the rho is the momentum. Feel free to call it rho-mentum if that helps. The weird variable symbols are going to continue. We have a letter J in this chapter for no clear reason. I can't talk for some reason. But the formula for momentum is rho equals m times v. The faster something is moving, the more momentum it has, meaning the harder it is to stop. That's why I put the train on the previous slide. Similarly, the more mass something has, the harder it is to stop, right? You wouldn't even want to jump out in front of a very slowly moving train, would you? I hope the answer is no. So those are the two main things that contribute to momentum, mass and velocity. If you have a lot of either of those things, you tend to be very difficult to stop. And we will begin applying that information to math and real-world examples. Since momentum is a new variable, a new thing to measure, again, want to include everything you need to know about it. Momentum, variable is rho. It is a vector. Momentum points in a direction because if you're moving, it's in a direction, and your momentum wants to keep you moving in that direction. And it does not have its own unit. The unit that physics uses for momentum is kilograms times meters per second. We didn't give it its own. And there isn't really like an American unit that is commonly used for it. I mean, I guess you could use, I don't know, pounds is different, weight is different than mass. There is not a good American unit for momentum that I can think of. Not one that you would have heard of before. Kilograms times meters per second. And that unit is literally just the two units you put in this formula, kilograms times meters per second. So it may not have its own word, but I feel it's at least one that's easy to build from the formula if you don't remember it from scratch. How do I feel so far? All right. So that's a new formula, so let's get in a small amount of practice for it. I have 4 different objects/scenarios listed on screen right now, and I would like you to very quickly work either on your own or with your classmates to determine which of these entities has the most momentum at their present mass and velocity. C? Anyone else vote C? Does anyone vote something other than C? D?
I'll
So
add
you
that.
have to convert.
Yeah, part of the catch, and this is me being tricky. I usually say when I'm not trying to trick you, I did put a little trick into this one. You have to check your units when calculating answers for technically every formula, but in this particular case, since the unit for momentum is kilograms times meters per second, you want to make sure you are using kilograms for mass and meters per second for velocity. So let's look at what these numbers should be. First is the building. Rho equals mv. This is the single largest mass up here, so you'd think it would have a lot of momentum, right? What velocity is stationary again? 0. Building's not moving, they don't tend to do so. So all that mass but no velocity is 0 momentum. A building is pretty easy to stop if it's already stopped. Make sense? Now, if the building is moving, you have problems for lots of reasons, but if it's not, which is usually the point of a building, then no momentum, easy to stop, we move on. Next is the arrow, which has the highest velocity listed up here at a whopping 1,000 meters per second. And a mass of 10 grams. What's that in kilograms? 0.01, very good. 0.01 times 1,000 is 10. So that tiny mass kind of nerfs the velocity by a lot. Next, the dog. 25 kilograms times 10 meters per second. Both units are actually what they're supposed to be this time around. So 25 times 10 is 250 kilogram meters per second. And lastly, a car. A lot of mass. However, this one's moving super slowly, 1 centimeter per second. So this would be like it's idling and you just don't have your foot on the brake. So a massive 200 kilogram mass. What is 1 centimeter in meters? 0.01, very good. Centi is 100 times smaller than base. So 100 times smaller than 1 is 0.01. And so 2,000 times 0.01 is 20. So out of all of these entities, the dog actually won. Because the dog has an average mass and is moving faster than the car. Again, to review, the building's already stopped, so it's very easy to stop. The car is moving incredibly slowly. Frankly, you could probably just put your foot on the bumper and that would hold it in place. I wouldn't recommend it, but you maybe could. Arrows are just comparatively small when compared to things like cannonballs and canines. And I will say from experience, I call her a puppy, but I guess she's about 3 years old now. My puppy is about 50 pounds of muscle in a torpedo shape. And so if that thing came bolting straight towards me and jumped at my chest, I would be on the ground. Dogs and other running animals have a surprising amount of momentum in them. So you can also think of momentum as a unit of how likely is this thing to knock you over if it runs into you? How's that feel? All right. That's about it for today. As we move on this week, we will hold on. You can back up. I've just got one small point I want to make. Because of the M and the V in the formula, a big mass or a big velocity can both contribute to momentum. Again, these are both things you wouldn't want running into you. I will also make sure to point out that momentum is similar to, but not the same as inertia. Remember Newton's first law of motion, object in motion wants to remain in motion. Momentum says something similar. If something is moving, it wants to keep moving in the same direction. The key differences between these two things is, one, momentum is a vector, so it cares about what direction you're moving in. Inertia technically doesn't. Inertia just cares that you keep moving, doesn't care if it's in the same direction or not. Two, you have inertia when you aren't moving, but you don't have momentum if you aren't moving. If you're not moving, your momentum is zero. You're very easy to stop because you've stopped. But your inertia is what's telling you to keep staying still. If you are moving, both your inertia and your momentum are telling you to keep moving in the same speed in the same direction. But momentum is powerless if you're stationary. Inertia is the one that persists at a constant level whether you're moving or not. So they are similar but distinct. They're kind of redundant, if I'm being honest. They're both two security systems making sure that these principles work right. So that's why there's a separate word for it. It's like inertia. It's like inertia, but it isn't. And next week we're going to talk about a secret third thing that's also similar that is still somehow different. So stay tuned. Any questions for today? All right. If you have any questions, report to lab this week as per normal. Have a wonderful day.